Good morning, everybody. I'm David Tetley, Director of Embedded Solutions at Elma. It's a pleasure to be here at my first Embedded Tech Trends event. I'm going to talk about something slightly different today, and I'm going to talk about bringing the App Store to embedded computing systems and how SOSA is defining the software framework for deployed applications to really make this a reality. So, like a number of you, I'm just going to start with a bit of a recap of history here. Embedded computing based on open standards has been around for almost 40 years now. The first VME boards coming out in about 1982, VIDA being formed in 1985, and then adoption of VME over the next 10 years, culminating in selection for some major military programs. But VME supported a wide variety of processors, and along with them a wide variety of software solutions, from bare metal to bespoke and proprietary operating systems. It also had a limitation in that it didn't provide the high-speed interconnects required for distributed computing that is needed for, or was needed for processing intensive applications such as synthetic aperture radar and EW and electro-optical and IR processing. So a number of vendors created their own solutions using the P2 connector, high-speed serial switch fabrics, which along came with them sort of bespoke software solutions. So it really led to what I call the Wild West of software architectures, where applications were very tightly coupled to the underlying hardware architectures and the software infrastructure, bespoke layers on top of the hardware, and it made the applications not portable and really limited their reuse. Now, OpenVPX came along in 2010, and it provided these high-speed fabrics. So it solved that problem, but it didn't solve the problem of interoperability and portability due to the broad spectrum of profiles. And I think Greg mentioned there was 93 VPX profiles, and then different protocols, a broad spectrum of protocols and user-defined options. So, but OpenVPX being adopted over, and there's still some legacy applications that have stayed on things like VME and compact PCI, but particularly in the military, OpenVPX has been widely adopted. But then SOSA came along with the goal to sort of hit the panacea of plug and play for VPX, and really solve this interoperability problem. So SOSA defines a technical standard from a systems perspective. It obviously covers the hardware, and from a hardware perspective, it sort of tightens up the OpenVPX spec by, from the plug-in cards, it limits the slot profiles, it standardizes the mechanicals and the cooling, tightly defines the connectors and the interconnect protocols. But it also defines things like the chassis and backplane and other infrastructure, tightly defining the backplane requirements, clock topology, and also defining things like chassis management. So, as well as hardware though, it really goes into a lot of depth defining software. And one of the keys here is defining the platform on which all the SOSA-based SOSA sensor applications must run, and that is the runtime environment profile. So it defines 3 runtime environment profiles, which I'll talk about in a minute. It also defines the infrastructure for management of the hardware and the modules via the system manager part of the specification, and also the management and coordination of the mission operations via the task manager. Now, along with this, it defines the architecture and in terms of the modularity of how applications are built and the interactions between those modules and the software interfaces between those modules when you're building a SOSA sensor application. So it tries to standardize this communication and interaction between these modules, and it also has adopted other standards. An example being it's adopted the Moira standard for the RF signaling layers of the SOSA architecture. So let's look at the runtime environment first, and it defines 3 runtime environment profiles. The first one, it's leveraged the face operating system segment runtime environment. This is the sort of core runtime environment for SOSA, and it leverages multiple face profiles plus POSIX and ARINC 653. But it also defines a profile for a containerized runtime environment. Containers are now a very popular way to deliver software capability. And it also allows you to deliver software capability that may not align with the face interfaces. And finally, it defines a runtime environment for virtual machines. And this is important because it can support you can run other OSs on a virtual machine, maybe support legacy programming languages and dependencies, things that don't align with face. But also it supports a type 1 hypervisor, which can be very important for safety critical operations because it allows for safety critical partitioning. So the key thing is these runtime profiles define the constraints and dictate the interfaces that application developers must adhere to in the creation of highly portable SOSA modules. And really, the defined runtime environments lay the foundation for that app store concept that I started with. Let's take a look now into system management. And system management standardizes the management of health, operation, and configuration of the platform and its security. And 60 pages of the SOSA Technical Standard are dedicated to system management. That's 13% of the document. So it goes into a huge amount of depth on system management. And if you look at the graphic here on the left, is it on your left? Yes, it is. It breaks down system management into functional groups. And if you look at the hierarchy, it's about managing the sensor and managing the sensor security, and then breaks that down into managing the sensor health, the sensor operations and its configuration, and then further distills that into managing things like sensor state, the mode, sensor configuration, also security aspects in terms of authentication, etc. If you look on the right, the architecture of a system manager, it's a client-server architecture. So it really consists of a set of agents, and these are the software entities that provide the services for this system management and for managing these functional groups. And then the managers which interact to these agents. And these managers can also, they manage the functions, but also can provide a user interface. So if we dive a little deeper into system management here, SOSA defines system management interactions for 6 different elements of a system. And there are over 250 interactions defined. And these must be supported by the agents provided via REST APIs. Now, REST is a sort of software, it's not a protocol, it's sort of a software architecture for moving metadata, and it's traditionally used in web-based applications. And these agents provide these APIs via what's known as RESTful endpoints. So it's a lot of software that needs to be built to support system management and support the specification. And if you take a look on the right, I've sort of developed a busy graphic that shows the 56 different interactions that are defined for the system manager module within the SOSA specification. So this brings an opportunity. So developers of SOSA sensors, their core capability is developing the application. They want to spend their software investment, put their software engineers on developing the application, and that's their core IP. They don't want to put a lot of effort and money into developing infrastructure. So it brings an opportunity for vendors who are developing and providing some of the hardware elements and system integrators to provide some of these software modules. So if you look on the system manager components, there's all the different agents for managing the different functional groups, and then the managers associated with these agents that interact with them and also potentially provide user interfaces. These are all opportunities that can be brought to the table by third parties. And then also, if you look at the wider SOSA sensor architecture, there's the task manager module. There's a whole load of support modules that are there to support the overall application and the operation of the core application modules. For example, security services or calibration services. So there's a lot of opportunities there for software development and modularized software blocks. So why is this important? Well, we need to remove the barriers for SOSA adoption. And if you look at the US Army and the CMOS initiative, that's accumulated in the CMOS mounted form factor standard. And that dictates SOSA and Moira standards to really to really sort of satisfy the goals of openness, standardization, harmonization, being aligned and adaptable. But the final one, cost effective. That's a real challenge when you've got a lot of software to develop. So it's very, very important that that doesn't become a barrier. The perception of the software complexity of SOSA and people porting legacy stovepipe RF applications to the SOSA architecture and also having to include system management, they may see it as prohibitively expensive. So we need to remove those barriers. So if we just dive down to a bit of a level of detail here, I'm not going to go into it in a great number of detail, but if you look at sort of a typical application within a CMFF system, a software-defined radio, for example, this is showing the hardware architecture, 3 PIC cards that are satisfying a software-defined radio application, and then the software modules mapped onto that, and you can see it's really quite a complex architecture. Including the RF and the Moira side of things and the system management modules. But all the blocks shaded in the 3 different shades of blue here show software modules that provide a opportunity for PIC vendors, system integrators, or third-party software vendors to provide modular software building blocks, really to help SOSA sensor developers satisfy the SOSA specification. One final point before I wrap up. A memo from the Pentagon released the end of last year, really dictating the use of MOSA across all military programs, signed by secretaries for the Navy, Army, and Air Force. So, they specifically call out SOSA, they specifically call out victory, and they specifically call out face. So, it's going to be very difficult for developers or the primes and people supplying these solutions to the forces to avoid these open standards. So what are the key takeaways? Well, the SOSA standard defines the software platform on which applications must run and how they interact, and it also defines the framework for system management. And successful implementation of the standard can provide a platform for truly plug-and-play applications, hence realizing the App Store concept. However, since the system developers want to focus their software resources in developing their own IP, they don't want to develop SOSA software infrastructure from scratch. And for widespread adoption, software alignment with SOSA needs to be affordable and have minimal impact on schedule. So pick vendors, system integrators, software vendors, can provide building blocks to satisfy key elements of the standard, and then reducing cost and risk. That will really be the key to SOSA adoption. And thank you very much. Thank you for listening. Any questions?